Today we're going to see the introduction or a review, I should say, of three-dimensional dynamics of rigid bodies, because this is the background that we need for the basic principles of the dynamics, vehicle dynamics. So let's get started over here. I have on this outline, it's a review of 3D kinematics and then later on introduction to Nastran 4D, now that it's called SimWise 4D. So let's disappear from here and let's get started over here. So in the case of a rigid body, we have a situation here. A rigid body, meaning, the points on the body don't move with respect to each other, because this is a solid rigid body and you have this shaping here. And in here we have this, XY and the Z axis, right-handed coordinate system. And you have, the question here is if you have this angular velocity here and rotates this body about the Z-axis, what's the velocity and acceleration of P? That is the question. Okay, so what we need to do in this case is let's make another sketch which now has a little bit more of the equations that we need. In this case, you have, as I said, this rotation here. You could see just by looking at it and seeing how things move that the velocity of P is going to be tangent to the circle that P describes about the Z-axis. So if this would be in this direction like this, maybe you should say like that. Yeah, that gives you the idea. So in this case, if we consider a rotation about a fixed axis, which is what this is, you will see that you have this vector BP in there. BP rotates like that. Yeah? And then it follows that the velocity of P that we're looking for is the distance of the arc divided by time, so ds dt. So S would be a measure of the arc that P describes. That would be ds dt, but ds dt is equal to r theta dot times sine of phi. So that's how we would do it. Yeah. But let's take a look at it here. The velocity of P is totally perpendicular to this to the vector BP. So in here, let's see if I can get some in here. There we go. We could just write it over. No, it didn't work. Okay, now it did. See, because I can write it, and maybe I should do it with the red pen. Blue, red pen. So if you have omega, which is the SDT is R theta sine of phi. That would be like this. This would be the velocity of P. I think it's important to be able to see that. You can also write that the velocity of P is the variation of the vector R dt, because R does not extend, so it doesn't change. So R dot is 0, but the change is controlled by this product, omega cross R. So omega is, cross R, where the vector omega is about the z-axis. So the conclusion of this is that for a rigid body, this is the equation here. For a rigid body, the velocity is given by omega cross R. It doesn't have a relative velocity term because this is rotation about a fixed axis. Okay. You see, for the rigid body, we can very easily conclude that the velocity is omega cross R. But if you differentiate this equation, omega cross R, to find out the acceleration, this is what you get. That the acceleration is alpha cross R plus omega cross R. Only these two terms. Okay. Does everybody see why A is alpha cross R plus omega cross R? If you don't, raise your hand so that we can explain. I'll ask my question again. Can you go from that expression that says velocity equals to omega cross R to the other one that says that A is the tangential acceleration valued at alpha cross R plus omega cross R, which would be the normal acceleration. So, any questions about this? So we're basically establishing right now two equations, one for the velocity and the other one for the acceleration. But maybe it might be a good idea to review that unless everybody is okay. So the acceleration of this point is alpha cross R plus omega cross R. We don't have any of the Coriolis terms in here or the relative acceleration because it is a rigid body. So obviously it's gonna have an acceleration tangential like this and one normal in this direction. So is the conclusion here that in 3 dimensions the displacement of a rigid body with a fixed point about the axis through O would generate an equation for the velocity of the point P, which is omega cross r. But also would generate the acceleration of that on the tangential acceleration alpha cross r, but also a normal component which would be omega cross r. Okay. Any questions about this? Hmm? Let's continue on in here. If you have a rigid body and you have it, you have a reference frame in here, we need to find an expression for the velocity and acceleration of any point on the rigid body by knowing the velocity of acceleration of another point. So in this case, we are going to join the origin to the point A, and then calculate the using the point B the velocity of B with respect to A, using this to find the acceleration. So what we have in here is that the velocity of a point is the velocity of another point plus the relative velocity between those two. This is a very basic principle of kinematics. The velocity of B then becomes the velocity of A plus omega cross RPA, where the angle omega is the angular velocity of the body at the instant considered. The acceleration of B is, by similar reasoning, the acceleration of B is the acceleration of A plus the relative acceleration, or the acceleration of B is the acceleration of A plus the relative acceleration between the two of them. And then we will add the relative acceleration, which now has a tangential component and also a rotational component. So that's
Good question.
yeah.
Is it rotating about point A? Or is it just rotating?
What is important here is that the velocity of B is the vector A, the velocity of A plus omega cross RBA. RBA means R of B with respect to A. Okay? The acceleration, we have the acceleration of B is the acceleration of A plus the relative acceleration. That's fine. Now you have, in this case, acceleration of B is the acceleration of A plus or alpha cross R BA plus the other one, which would be omega cross R, which is the normal acceleration. Okay, here we can also have a rotating frame and express it in terms of unit vectors that indicate the directions of little x, little y, and little z. This is an example here. that shows that the velocity of P and P prime so it derives omega with respect to a fixed axis. Am I right? All we're saying here is the velocity of any point is the velocity of another point plus the relative velocity between those two. There we go. These are all the components that this analysis produces. Like one, it has the absolute acceleration or, well, no, the relative acceleration. Then you have acceleration of p relative to the moving plane. And so we have the vector acceleration. In this case, would be the acceleration of another point plus the relative acceleration of p with respect to z. Okay.